Yeah, so I didn't go on Friday. Was it interesting? So the day after the day. Okay. So that's much dynamic goals oh wow, okay. But they are I think they say actually have more survey we're gonna use that we're gonna use yeah, the whole part of the competition itself is kind of like a bit unclear. Also, each size is how are we gonna make all the work on single PI versus 20 PI. It's kind of yeah. That's centralized and everyone. Yeah. Yeah. The user experience.
Maybe explain themselves. In represent take
Oh, hi guys.
Agent.
Actually, like, yeah. Oh, yeah. Oh, yeah, actually, I didn't look at the email because I had like a lot of meetings.
Okay, so let's get started. It's our great pleasure to have Furong here. Furong is an assistant professor from University of Maryland. She has been doing lots of very interesting great works on trustworthy machine learning these days. So let's welcome.
Thank you for having me today. We'll be switching topics a little bit. I'll talk about how to build foundation models for sequential decision making, and specifically, I'm choosing the application area of robotics here, since I know a lot of faculty and students here are interested in robotics. So it's basically, different from what I usually talk about, trustworthy AI ML. But okay, so in some sense, it's still related to trustworthy AI ML. I'm mostly thinking about the seam to real gap, that a lot of you are not unfamiliar with, how successful reinforcement learning is, right? When it comes to applying it to simulated environments and all the success stories, I don't need to reiterate. But when it comes to real world, what is really going on is that there's all these uncertainties. Here is an example that actually I stole from Roberto. Having a simulated environment that is mimicking the real world, and hoping that if you learn a good policy in a simulated environment that is supposed to be exactly replicating the real world, you hope that in real world, it will have a very high success rate, right? Because, the success rate in the simulated environment is supposed to be high. Does that really happen? So here is what's going on here. If you look at the success rate in the simulated environment, if you use an RL algorithm, it's not perfect, but it's decent. 40% success rate is actually not considered pretty low in robotics, because robotics is very challenging, as you all know. But I wanted to ask you, not including Roberto, because he would know the answer, what is the success rate of real world with this trained policy? Any guesses? 5%? 0. You must have been, seeing Roberto's talking about this before, so it's actually 0%, which is considered, you are supposed to be surprised about this 0% number. Yeah, so we all know there is this huge sim to real gap, but how do we close the gap? It's something we'll be exploring today. All right, so what really happens in real world environments is that, you see there's all this ever-changing environment, right? So, you may have a rainy day. That is not necessarily how your autonomous agent is trained during this weather condition, or even more extreme weather condition of like storm or something, or blizzard. You also see that, very occasionally there are like natural disasters, right? There are this very extreme distribution shift that occurred to us, and COVID-19 is a great example of that. So in this ever-changing world, data is really expensive to collect, in the sense that, because it's always changing, because all these tasks that you have to deal with, all the variations, you sort of have to continually collecting data in some sense, make real-time adjustments. But also in the same time, if you consider all these kind of models, right, like, imitation learning policies or RL policies, they're very expensive, hard to train, especially if they're powered by these gigantic neural networks. So, of course, how do we deal with this unexpected changes and adapt to the environmental changes is something, this talk is aiming to tackle. But if you step back a little bit, everybody is talking about foundation models these days. What is a foundation model? You see this remarkable transferability or generalizability out of these foundation models for NLP and for computer vision, right? So, you have this multi-modality data that is fed to a foundation model, and it works very well. But the question here is that enough for us to use in terms of robotics, for example? Is that enough for us to close the gap of sim to real? right? So in this case here, rather than these modality data, you may have diverse sequential data, such as the trajectories you've collected from these embodiments. Then the real question is, can we build foundation models that have this remarkable capabilities of adapting to downstream tasks, very diverse downstream tasks, and being able to have this so-called autonomous AI agent? Is that something that's possible, right? And would that be possible using, for example, just these language model, for example, large language model or vision language model? Okay, so that's something we'll be asking today as well. Okay, so in order to ask that question, in order to have these foundation models for sequential decision making, maybe the first question to ask, as we already alluded to, is next token prediction language model enough to deal with the sequential decision making process, right? Which involves like this transition dynamics between states using specific actions. You have to learn, the transition dynamics, but you also need to learn this policy of what action leads you to a final goal, right? So, but in order to answer this question, I wanted to ask a simpler question, which is large language model enough to deal with time series? You all know time series does not have to necessarily involve actions, right? So there is not necessarily this complicated transition dynamics you have to learn. No action, right? So in this simpler case, would the language model do a good job? Unfortunately, based on this paper that published earlier, you see this huge gap, even for very simple time series reasoning tasks. You see this huge gap between what human beings are capable of versus what the best language model is capable of, right? So I'm not gonna go too much into details, but the punchline here is that intrinsically, these large language models, although showing remarkable adaptability in natural language and computer vision, they are they're intrinsically limited for sequential decision making, such as time series that require some reasoning. Okay, so given that, this sounds like a really negative message, right? So what do? Before that, let's ask the question, what really makes a good foundation model, or what makes good foundation models for sequential decision making? I made a wish list, and people may agree with me or not, but mostly I think there are three very important key characteristics or desirables I really want. First is versatile, right? So you want it adapt to very diverse downstream tasks and algorithms. Whether it's zero shot or few shot, that's a different story, but is able to quickly adapt to very downstream tasks. But more importantly, it's also kind of, diverse in terms of the tasks, in terms of the embodiment, in terms of like the noise in the sensor and stuff like that, right? All these kind of seem to rail gas. So that's number one. Number two, I would argue that the generalizability is the key, right? So you really want to make sure that you trained on certain tasks in certain domains, but it adapts to unseen tasks and domains. And that's really important for this thing to be called foundation models at all, right? And then third one is almost like a bonus, that what if this foundation model doesn't have to be trained on highly curated data, but rather, let's say, low quality, noisy, random data? Am I asking for too much? Let's see. So in order for the first one, right? So it's not surprising based on this, like almost a consensus that in order to build such a model, you wanted to have a pre-training phase that has a lot of tasks, a lot of diverse data. And more importantly, not only the quantity, but also the diversity, right? So you wanted to have a lot of tasks, but they're also very diverse, covering a lot of support in some sense. Okay, so I think that's not very controversial. Also, you would argue, I really hope this is reward-free. Why I say that is because a lot of us are coming from an RL background, and in RL there is always this MDP model, this tradition of like having a dense reward guiding you through the process, right? I argue that that's a little bit unrealistic to assuming that you would have reward signal guiding you through, unless you're able to build a good reward model for a specific domain. That's a different story, but we're not going to go there today. So I would argue it's reward free, mostly for the reason that I want it to be conflict free and generalizable. Okay, I've talked about generalizable, but I mostly here focus on versatility, right? So what about generalizability and resilience? So basically, I argue, before that, I argue that these pre-training of like diverse tasks or like so-called simply scale up to see this emergent behavior is probably not very easy for robotics. I feel we're at this, domain, we're at the regime that the number of tokens that we, fed to the foundation model is still in a very low regime, so that we wouldn't see this kind of emergent behavior anytime soon. Okay, so that is one thing that I think we still need to do something to make sure there's this generalizability and resilience in addition to this scale everything up. Okay, so what is that? And today, based on the talk title, you probably guessed I'm going to talk about world model. And specifically, I'll tell you what exactly I mean by world model. But nonetheless, let's talk about the paradigm of this so-called foundation model. You have data collected from diverse tasks and domains. That's not, questionable. But you go through this foundation model for a training process. You do forward pass, do backward pass. But more importantly, you wanted to ask, what is the right pre-training objective function? By the way, I'm not going to talk about what specific architecture you want to use, like, what is the model architecture of the foundation model. And again, you can talk about that for another day or so, because, faculty here have a lot of work in that area. I'm not going to talk about or argue about what kind of architecture, but rather I wanted to talk about what is the right pre-training objective function. Is next token prediction language model enough, right, for this kind of robotics task? So to zoom in a little bit, you can see, let's say we have a robot, right? So it observes something. So you see the world through sensors. I mean, here I'm showing like an image, but you could imagine there are like all kinds of sensors, right? So infrared sensors, LiDAR, radar, all kinds of things, GPS, and so on. So you see the world, but more importantly, you act. Right, so a lot of the things that are missing in existing language model is that it never models the action explicitly, right? Here you have an agent. You see the world, but you also act to the world so that you change the world in some ways, right? So what that really means is that you would have a world model that's based on the specific action, you will lead to another state. And based on that state, again, you can act and go to another state and keep doing that. And finally, you may be getting a reward because it's kind of a sparse kind of feedback whether you've succeeded doing some specific task. So that's what I mean by by world model. You can see there are two things here, very important. There is the action, that is acting on the observation. That's very important. But you also notice that I sneaked in this kind of encoder there to put everything in latent space. And I argue that the reason why I wanted to do it is the real observation could be very noisy. And you sort of wanted to map everything in a more compact space for the denoising purposes or for a more compact representation, so that your world model is essentially working in a latent space rather than in the actual observation space. Any questions? Yeah.
So I understand this world model is really like a delayed reward in an RL setting. Am I correct?
Well, you could also argue that you can, take that reward out. Here, I want to focus on is like this transition dynamics of like explicitly modeling the action here. Different from like, for example, Sora. When Sora is coming out, everybody's saying, oh, this is the world model. I totally disagree with that because there is no action taken care of at all.
We need some sort of common action space because for images.
That's a great question. I'll get to it. Right now, you could assume that we're living in an ideal world that every action space is unified, which is impossible, but okay, so far so good. So let's move on. Basically, yeah, sure.
That the sizes are not that big. So why don't use NLP?
Sorry, what sizes?
Something that the
number of tokens
are less, maybe it won't be even chinchilla optimal, like 20 times the size of the model, which is unavailable.
Yeah.
So why don't you use like NLP models as a base and then on top of it,
Yeah.
retrain?
Great question. Yeah, we will get to that. Yeah. Spoiler alert. Okay, cool. So moving forward, I argue here that in order to have a good foundation model, and in other words, choosing a good objective function for pre-training, this pre-training objective should respect the latent world model. What do I really mean by that? So here, basically, I argue that if you really want generalizability and resilience, a world model on latent space is going to help you in a sense that you're learning some common representation space that's good for you, and you're learning some basic, almost like basic laws of physics of how the world is working. And you're gonna, you could do imaginations about how the world is working based on this world model you have built, implicitly or explicitly. But the real question is, how do I design objective function that is going to respect this world model? So that's why I'm starting with this, kind of bragging name, smart. I don't know how smart it is, but at least it's clicking all the items that that are in my wish list. Basically, it's very versatile, adapt to downstream tasks. It's also, pretty generalizable in the sense that it can generalize to unseen tasks and unseen domains, which is pretty impressive. Given like the small, pre-training scale we are able to do in an academic environment. And also, I think as a bonus point, as I mentioned, it's really resilient in the sense that you don't really need to do a lot of data curation to come up with very expensive data for this model to work, but rather you could just use random policies, let the policy explore the world in a random manner so that you collect a lot of data in an effortless way. I think this is really crucial in the sense that, we don't really want to spend so much time collecting expert demonstration data in robotics. It's just like not very efficient and scalable. Okay, so how does it really work, right? The key is this so-called control-centric pre-training objective function, which has those three parts. I'm not gonna go into the mathematical details, but the first two terms are sort of like a short-term control term, which does like a forward dynamics prediction and backward dynamics prediction. You could imagine like masking out, the current action, masking out the next state and predicting it, or masking out the action that leads to the current state and try to predict it. So there's forward and backward prediction. You can see the forward prediction is almost like the same as like next token prediction in some sense, right? But in addition to that, you're going to have a backward prediction. So that's one thing that's different from next token prediction language models. But what's more important, actually, as we observed in experiments, that this long-term control is way more important in order for this to have a remarkable generalizability and to have this kind of temporal awareness of this world model dynamics, which is basically asking the question of what actions would you take to generate such a sequence, right? So you can see this intrinsically, masking out a few actions so that you could predict even in long-term, for those of you familiar with MDPs and RL, this is basically model-based RL controlling the compounding error over multiple steps in some sense. Okay. So you can see, basically using a traditional transformer, which, is the backbone architecture for language models, but we're not actually, using language models as initialization, but rather we're, training from scratch, but using these objective functions that are capturing the short-term and long-term control. So you can see the results are pretty okay, I would say, right? So you have some kind of, environments, everything is still in the simulator so far. You have some environments that's used pre-training, and then later on, you're gonna test on some unseen tasks as well. Well, you were gonna test on the task that you've already seen before. But in addition to that, you're gonna test something that is not seen during training. And can see the results are pretty okay. So you see better performance, you see generalizability, but more importantly, you see this resilience even to random behavior pre-training. And that's not surprising at all. The reason is that in order to learn the world model, you probably would better just have it random explore the world rather than having an expert policy telling you what to do exactly, right? So that is not surprising. But I think this is good in the sense that, at least we've figured out that next token prediction is probably not enough for us to do this kind of foundation model for robotics, right? So smart is good, but it still has some problem, as I didn't really talk about yet, is that you have this pre-training objective function, which basically tell you what is a latent representation space that you should work on to build policy network downstream. So in the sense that you still have to adapt to a downstream task using this latent space you've learned and then fine-tune your policy ahead. Sometimes you also even fine-tune the entire representation learning, pipeline as well. But the problem with that is so far smart still requires fine-tuning with very large number of demonstrations during downstream adaptation. For example, 50 shots, which is a lot considering each just trajectory could be like 500 steps, right? So we will get really bored teaching our robots how to do this for 50 times. I don't think that's realistic, right? So how do we deal with it? We come up with something called tackle. In case, I don't know if you guys are hungry, I'm a little bit. Temporal latent action-driven contrastive loss for visual RL. What it really does is actually quite simple. So let's say you have a state, right? So you go through a state encoder, you get a latent representation of that state, but you also consider a sequence of actions. You could also, encode these actions into an action encoder and get a latent representation of this action. But you're going to predict what is the next state after the k steps of taking these actions. You could imagine this is a long-term prediction, right? You're controlling the compounding error that you're accumulating over time. And more importantly, you're going to project them into some space and use a contrastive loss to guide the model into learning what is a good representation here. So in this sense, guiding through how to update the parameters of the state encoder and action encoder. And does it work? Actually, it works for a single task setting, which means that you get training data from this task and you're gonna test also in the same task. And it's pretty impressive in the sense that it is beating state of the art quite a lot by a large margin. So it's not just a kind of error band within an error band kind of improvement, but it's quite a drastic improvement. My guess here is that this kind of contrastive loss really helped. But in addition to that, we're also controlling the compounding error of learning these world model, although implicitly. But this kind of controlling of the compounding error using the sequence of action really helped in terms of learning a good representation for us to do downstream tasks. Okay, both for online and offline, you see some good results, but this is not foundation model, right? You would argue, Furong, this is not foundation model, it's single task RL, that's it. But we actually really made it into a foundation model by drastically improving the scalability of this contrastive loss. In the sense that you come up with a better negative sampling strategy. Before, you basically, in a batch, everything else that is not ST plus K is going to be a negative example, but now you're going to do some kind of smarter way of selecting it from the ones that are very close to ST plus K, but not ST plus K, right? So in the vanicity of it, essentially. Okay, so this really works, and especially is the key for scalability. And that's when we started to think, maybe this tackle objective could be used to build an actual foundation model. This is what is premium tackle. So you can see what we did here is in DMC, Meta World, and Libero. Actually, I think Yuka is not here, but this is one of the things he has been working on quite a lot. We do some pre-training. right? But we see remarkable generalization. Of course, you see like, in seen embodiments as well, but also in unseen, in harder tasks, and in long horizon planning problems. So how do we really do it, right? So basically, it's this tackle objective function that is contrastive loss that is considering this kind of compounding error in your world model. All right, so you can see it has like remarkable few-shot behavior cloning for unseen tasks. Both, here I'm showing the mind control suite and meta world. Also in liberal, you can see that it works pretty well compared with all the existing methods so far. Okay, so now, I'll also show you something like, generalizability to unseen embodiments, unseen views, and again, robust to low quality pre-training data. But there is a caveat here, if you think about it, which is, I've talked a lot about this pre-training objective function, right? Smart and tackle and premium tackle. But what knowledge am I really transferring? So far, what I'm really doing is that, in this foundation model, I'm learning a encoder that's mapping my raw state and raw action into some kind of latent representation. And using that latent representation, I could either learn a generalist policy, or I could learn a so-called universal world model. And based on this universal world model, we could do something, right? For example, one option is that, using this encoder, you're going to basically transfer the representation in some sense to new tasks. Or you could explicitly use this world model and using this representation space you've learned to do zero-shot planning adaptation. So these are two options we've been looking at so far in existing works. But what about this one? Generalist policy, right? This seems to be a little bit more ambitious in the sense that it's truly zero-shot, right? Out of the box. Can you build such a model that is basically a generalist policy that is able to deal with all kinds of tasks downstream? This is a first attempt. It's not from our group, is from the groups from Stanford and Berkeley. It's called OpenVOA, Vision Language Action Model. Okay, so it's basically fine-tuned from a vision language model, but it respects action. What it means is that you're fine-tuning this vision language model with robotics action. So you can see, they collected a lot of robot episode data. And then they were using that to basically ask the question of like, say, here is my state, and what is the action that I should be taking to reach a specific goal? And that goal becomes like a conditioning, right? So you basically are, fine-tuning a vision language model such that it respects the action. It's like, adapting to a policy. So the idea is very simple, but it actually works pretty well. I think the main success is you're utilizing the remarkable generalizability of vision language models and adapting it such that it can output action. Yeah.
Actually, I know you said this is not from your group, so I'm actually trying to understand. So does this multimodality really, so what is that is transferring? It's a good base.
I think it's the transferability here is that
so
your
modality matters. Let's say they would not have used rewriting, and let's say they would have used language. So is it? The question that I'm asking is it is transferring the modal representation to this robotic setting, or is it just a good base pre-training, which is just a better initialization for your next task, which is robotics?
I think the really remarkable transferability is coming from this vision language model being able to recognize anything in the image. Like they would know this is a robot, they would know this is a cup, they would know, in a different setting, this is a different cup in a different kitchen or something of that flavor. So, this kind of generalizability is basically like a symbolic representation from the images that you fed to these vision language models, right? But now if you fine tune it using robotic actions, it basically tells the vision language model, you shouldn't only be doing object recognition, you should be also doing some kind of, policy learning what kind of action would lead you to your target state, right? Your target goal. So that is what it's doing. You can see there is a lot of flaws. The first thing is, it has it's a very impressive generalist policy. It's kind of working out of the box, but it still struggles with spatial temporal reasoning. I'm supposed to give you some failure cases, but this thing is just under submission and actually scrambled to make some slides this morning. So I don't have that. Feel free to reach out to me to see some failure cases of OpenVLA. Based on that, basically the failure cases is, pretty much because this vision language model still struggle quite a lot in terms of spatial temporal reasoning. So based on that idea, we think, can we fix something, right? So what we did is that we're gonna, take some additional data, right? Some kind of, bridge and fractal data from this OpenX embodiment dataset. Oh, actually, fractal is this Google robot dataset. And we're also going to train this OpenVLA model using our Widow X250 real robot datasets we collected in our lab. And what's going on is like, we think if you don't have this kind of capability of doing like temporal spatial reasoning, can we do something to help you? And the idea is very simple. You just wanted to basically augment the prompting of this visual language model by adding this so-called visual trace. What this visual trace does is basically telling you what is the historical points of this very critical anchor point in my image. You can see that, we have a set of algorithms to decide which are the critical points. And then we have basically deploy an algorithm to figure out what is the trace of that critical point in the history. And simply just by that, it's amazing how this kind of, vision language action model is able to output, action tokens in a much more accurate way, sort of providing it with like spatial temporal awareness in a very low effortless way. So basically, and in addition to the original image, which is prompted to this vision language model, you use this image with visual trace. And then during deployment, you can see that, we deployed it in this simpler environment kind of simulator, but also we use the Widow X 250 real robot. So a little bit more details about what this visual trace is really doing. So initially, you would come up with a window, right? So like, of historical frames of this. And then you do some kind of multi-point tracking. And then you do some kind of visual trace generation using this kind of co-tracer algorithm that is already there, that is like, able to generate this visual trace prompting for us. And essentially, you just, use that to prompt the vision language model. In our case, we actually fine-tune the OpenVLA model and basically have this robotic control that is respecting spatial temporal reasoning. Okay, so some results you can see very quickly, in the simpler environment tasks, you can see compared with OpenVLA here is significant improvement, but also we made a very small model that is like 4 billion parameter rather than the 7 billion parameter. And in this much smaller model, we also did the comparison. It seems like it's also seeing remarkable improvement because of this temporal, prompting. Some more experiments showing the variations compared with the previous OpenVLA model. Here in the actual kind of real world robotics manipulation task, we did, folding clothes, swipe corn stink, pick place corn pods, and pick up knife. I can show you some demos here. It's very slow. We didn't do like a speed up of the video. I should have done that. All right, so basically you get the idea. It's out of the box. So I talked a lot about, foundation models, how to design pre-training objective function, what kind of knowledge to transfer. Do you want to transfer the representation, or do you want to transfer the actual generalist policy, right? So, but what I didn't talk about, which is coming back to your question, how do I deal with action, right? The actions could all be in very different spaces. Can I come up with an action representation that is also sort of, in some sense universal? But before that, actually, I wanted to talk a smaller problem than that. That seems to be a larger problem to me, but a smaller problem to me is like, we all know in robotics, action is very primitive level, right? Primitive action is very low level. But can we learn these skills autonomously from these sequence of actions, right? That has always been like, this kind of hierarchical RL problem, or, this kind of action abstraction problems out there. But what we did here is sort of a little bit unconventional. Here, I'm just motivating why temporal abstraction really helps data efficiency in learning, right? Because you wanted to learn these skills rather than actually always learn the repeated patterns in a primitive action level. So it's a very, important learning paradigm, right? Almost like hierarchical RL. But in order to do that, we make an analogy in language model here. And for those of you familiar with it, tokenization in language model is the key for the success of language model. I mean, you may argue that it's why language model fails in a lot of ways, but it's also the reason why language model are very successful in a lot of settings. It's because they were able to do tokenization, right? What does that mean? It means that the prompt, which, in its raw form is just, thousands of bytes in UTF-8 for very simple tasks, right? You could have very long, byte streams in a prompt. But really what language model does is it's actually treating the text byte stream as a sequence of tokens that is very compactly represented, such that in a very fixed window size, you can have more information fit into that window size in your context window. That's the key here. It's sort of like a compression mechanism that is tokenizing the very complex information into this token, codes, right? So similar idea here, that if you think about the skills and the primitive action in these kind of robotic trajectories, the idea is, can we learn these abstraction of these skills into tokens, right? And, we kind of take inspiration here. We think, oh, tokens are temporal abstractions of the byte value sequence. Then can we use byte pair encoding, which is how language model, learn these tokens? Can we use this same technique, byte pair encoding, to learn the skills in control trajectories? So that's the idea. And basically, it works pretty well. I forgot to put the results here. If you're interested, feel free to check out our paper here. I use the IFML paper. So I think this is a one step towards dealing with actions in an autonomous way, so that you learn the skills, group, the skills together using byte pair encoding. Okay, so I talked about this kind of improving planning efficiency from action to skills. But can we think about something out of the box here? Out of the convention here, which is, I'm going to talk about as something that is, I'm personally really interested in, is this meta policy learning. Now, if you think about it, you might think, oh, this is just a meta learning, right? Everybody is familiar with meta learning. But I'm going to frame it as like meta policy learning using generative AI. What do I mean by that? More specifically, I really mean meta policy generation using generative AI. So imagine you have this text to image models, right? Diffusion models, for example. You can have like a robot arm picking something and stuff like that. Like diffusion models are really powerful. It's arguably the state of the art in terms of text to image generation. But the question here is, can agent behavior be used as a prompt for policy network generation using a diffusion model? Right here specifically, let's say you have this behavior, right? So you have these trajectories that you've fed to like these models. Is it possible that you use a diffusion model to generate policy network parameters that can later on be deployed in actually implementing these tasks or solving these tasks. So that's like a level of like meta learning in some sense, but using the remarkable generalizability of diffusion models. So you can see here, actually, as a spoiler alert, this is a Unitary go-to robot that is deployed using such a framework. The policy is basically generated from a diffusion model with a specific prompt. Okay, so how do we really achieve this? So here, the policy synthesized on parameter spaces, you have this trajectory data. We're going to use as a condition. And then our algorithm is called make a agent, which essentially through this diffusion model, you'll be getting this policy network parameters. How do we do that? Specifically using one trajectory data. And sometimes it could be like a suboptimal trajectory, which is really interesting here. You would imagine that, better you put it at expert demonstration, and then this diffusion model would synthesize or generate a policy network parameter that perform very well on robotics. How do I do it? So basically, the idea is train once for all. We have some training data set from Meta World and the Robot Suit, whose founders actually in the audience, or some of them are traveling. So you have this multitask learning using 13 tasks. And then you are going to test on some unseen task and robotic generation. We also tested on real robots as you see, which I will show you later. So here, what it does is, during real world deployment, for example, we ask, can you avoid stepping on a banquet while moving around the mat? This is like 0 shot, okay? And here also another example, navigating to circumvent the goal and ball swiftly. Sort of swiftly, it's questionable. But what it really does is, given this trajectory data, which is a expert demonstration. Yeah, 2 more minutes. So you have this behavior embedding, which essentially is using tackle as the objective to train a representation that is compact. And then using that representation as a condition, you feed to the latent diffusion model, which is like the text prompt of the diffusion model. And then from Gaussian noise, you can just generate, using the denoising process, generate this latent parameter representation, going through a autoencoder and decode it through this decoder to get the synthesized policy network. This is how it works. And very interestingly, this diffusion model is not really like memorizing, but it's sort of like generating new things. You can see here, we're making a contrast between like the generated policy perform different behaviors compared with the prompted behaviors. Okay, so that's the end. I talked about how to do pre-training objective functions. We talked about smart tackle, premium tackle. We talked about what knowledge to transfer, the generalist policy of trace VLA. We also talked about how to improve planning efficiency using price, and sort of out of the box thinking of using a diffusion model to do this kind of generalist policy generation. And with that, thank you. And I wanted to thank all my students who made all the work possible. Thank you.
Any questions?
I wonder if any of the work you've thought about partial observation or partial observability and how that might impact the framework. I imagine you could have like state alias, observation aliasing, which might be challenging for Taco.
I would argue in the real world deployment is already partial observation in some sense, right? Because your sensor is only able to capture, not the whole world, but in some sense, a snapshot of the world.
Many of the tasks for manipulation, right? I mean, it's fairly observable.
Oh, for example, this kind of go to the unitary go to of like moving around in a space. I think that's sort of, but I get your point, which is maybe we can intentionally put some noise in the training or in the observation space and see how to